Last time we looked at this idea of the unified atomic mass unit, U. Can anybody just say what U is? What? Okay, that's right. So we have the U. They took a carbon 12 atom, the whole atom, including the electrons and so forth. So they took a carbon 12 atom like that, and they found the mass of it. They found the mass of this, and they divided it by 12. All right? And they got a number, and this is the number over here, 1.61 times 10 to the negative 27 kilograms. So that equaled 1.661 times 10 to the negative 27, 10 to the negative 27 kilograms. And they said, well, look, that's much too small. We don't want to talk about something like that, negative 27 kilograms. We decide to call this U. That's 1U. And that's your unified atomic mass unit. And because of that, because they could, because they applied it to carbon, they could take it up. All the other things are relative to carbon. Now we can talk about it in kilograms. That's our usual mass unit. But when we start going to very small, we like to work in EV. We can also talk of it as 931.5 mega EV C to the minus 2. Now this is also a mass unit. This is a mass unit, all right? Because when I put it into my energy formula, E is equal to mc squared, and convert that into an energy, then I get, if I just take the unit part, now obviously the mega corresponds to 10 to the 6, it's a million. The unit part is this, so if I put that into my formula and I have EV C to the minus 2, and then I have my C squared, obviously the C squared and the C to the minus 2 cancel, and I'm left with my EV, which is an energy unit. So your energy unit is the EV, alright? This U, if you converted that all to energy, and in terms of energy, it's 931 MeV. Alright, in terms of energy, in terms of mass, it's 931.5 MeV C to the minus 2. Does that make sense? Are you okay with that? Alright, it's a little bit of a tricky thing. Now, if I want to take that as an energy unit, so if I've got 931.5 mega EV, that's so, this is, if I wanted to make this mass, I would have to put in that amount of energy to make that mass. Now if I wanted to convert that to joules, then I've got to multiply that by 1.6 times 10 to the negative 19 coulombs, and I make that into a joule value. Alright. Okay, so it's really important that you've got an idea that you're going to be working with this. Now, as I said before, what's really important, if you take the mass of a proton and the mass of a neutron, now the carbon 12 isotope, the nuclei that we're dealing with, carbon 612, has got obviously 6 protons and 6 neutrons. So it's got 6 protons, 6 neutrons. So it would be 6 of these, that over there, and 6 of these. Now as you can see here, over there, these are slightly more than a U. Alright. So if you took the separate parts of a carbon 12 atom of the nucleus, took them all as separate parts and said, okay, let me bring this one here. You squash them all together, make them into a nucleus, they lose mass. Well, that mass turns into energy. They actually go into a lower energy state. They're like they're all living on top of the valley, and they all go down into the valley. They lose potential energy basically. They go into a a lower energy state, and they go into such a deep valley that they never want to come out. They stay down there. Yeah. That's nuclear fusion. That's exactly what's happening, as Andy says. That's nuclear fusion. So in the sun, what happens is that you are pressing protons and neutrons together to form, firstly, they form hydrogen ions are pressed together, and they form things like deuterium, which is a hydrogen with a proton and a neutron, tritium, which is a hydrogen and a proton and two neutrons. Then it forms helium. All of this is giving out energy as it's taking place. Okay, so the mass differences there is converted into energy.